Parts of the universe have the same temperature, yet they never touched. That mismatch is the horizon problem, and inflation solves it. Today you'll see the problem visually and understand why it matters. Look up at the microwave background, a smooth, glowing dome. The cosmic horizon is the region light could reach since the Big Bang. It matters because it limits which regions could have ever interacted. Light travels through space, while expansion carries regions further apart. If parts are separated beyond that reach, they could not share information. For example, two patches 30 degrees apart in the sky never exchanged light early. So the horizon defines where causal connections could exist. A full sky map of the microwave background looks like a pale mottled sphere. That map shows temperature nearly uniform across the visible sky. This uniformity is puzzling because distant patches could not have exchanged heat. Photons last scattered when the universe was about 400,000 years old. Interactions ended then, freezing the pattern we now observe. The causal horizon then was tiny compared to today, linking only small regions. So the CMB's uniformity sharpens the horizon puzzle. Picture a balloon dotted with paint, swelling under warm light. Each dot represents a patch of space moving apart from neighbors. Expansion increases distances, while light speed stays the same. Space stretches and moving coordinates remain fixed. Photons cross fixed physical distances slowly relative to expansion. At recombination, causally connected regions span a few 100,000 light-years. So the balloon picture makes the causal limit easy to see. A silent dish scans a cold black patch of sky at night. Satellites measured that faint microwave glow with extraordinary precision. Those measurements revealed tiny temperature variations across many angular scales. Instruments compare temperatures between different sky directions repeatedly. Then they compress measurements into a power spectrum for analysis. The power spectrum shows which angular sizes have more structure. For example, the Planck satellite mapped fluctuations down to microkelvin levels. So precise measurement turned a visual puzzle into a quantitative problem. Close your eyes and picture a tiny, perfectly mixed patch of space. Inflation was a burst of extremely rapid expansion early in the universe. It matters because it can stretch that tiny uniform patch into our visible cosmos. During inflation, a small region reaches thermal equilibrium quickly. Then expansion carries that uniformity across enormous volumes. Quantum jitters inside the patch get stretched into galaxy seeds. For scale, inflation must expand space by at least e to the 60. So inflation explains how widely separated regions share the same temperature. A panorama of sky surveys glows with countless data points and contours. The horizon problem sits beside other initial condition puzzles in cosmology. Solving it with inflation raises fresh questions about how inflation began. When inflation ends, reheating dumps energy into particles and photons. Details of reheating depend on particle physics we do not yet know. Models need at least 60 folds of expansion to match observations. So inflation fixes the horizon while opening new experimental questions. A tight detector array watches polarized microwaves from the infant universe. Polarization patterns carry signatures of processes during inflation and reheating. Detecting a swirl pattern would indicate primordial gravitational waves existed. Instruments search for that B-mode pattern while they fight foreground dust. They also battle instrumental noise with calibration and redundancy. Combined observations have pushed limits below 1/10 for key amplitude ratios. So polarization offers one of the cleanest experimental probes. A cinematic sweep moves from a tiny hot spot to our full sky. That tiny spot, perfectly mixed, inflates into vast causally disconnected regions. If that early smoothing did not happen, the sky would look wildly different. Heat equilibrates inside the patch, then inflation stretches the patch outward. Reheating then fills space with particles and photons, creating the CMB. Tiny fluctuations of about 1 part in 100,000 seed later structure. So the visual story ties initial smoothing, inflation, and our smooth sky. Remember, inflation explains why distant patches share the same temperature. If this visual explanation helped, consider subscribing for more cosmic dives. Net result is a tiny uniform patch, rapid expansion, and our smooth sky.